So let's take a look at a problem that employs lots of different properties of exponents. Our problem below has both positive exponents and negative exponents in it, and there are many ways to simplify this expression. Your job is to just pick a way that you're most comfortable with and go with it. For me, looking at this expression, one thing I might decide to do is I might decide to go ahead and simplify what's inside my parentheses first. That is, I have a quantity with 5x to the negative 8 y to the negative 2 divided by 15 over x to the 10th y to the negative 7th. And I'm going to simplify that quantity first. So let me write down what I have. I have 5x to the negative 8, y to the negative 2 on top, and then underneath it I have 15 x to the 10th y to the negative 7th. And I'm going to start there. Then I'll worry about afterwards applying the negative 3 power to what I get. So starting on the inside, I'm first going to focus right here on my coefficients, my numbers in front, 5 and 15. Notice 5 divided by 15 is a fraction, and both the numerator 5 and the denominator 15 are divisible by 5, meaning 5 over 15 can actually be reduced to the fraction 1/3. So one way to think of 5 over 15 is 1 over 3. So I might start right there and simplify that first. Then I'll take a look at the next part, which is the variable of x. We have x to the negative 8 on top, and then we have x to the 10 on the bottom. That is, we have a quotient, right? A quotient of two bases that are alike. And so the rule that we can use to simplify this kind of expression is what we call the quotient rule, right? The quotient rule allows us to take like bases in the numerator and denominator and simplify them. And the way the quotient rule works is it says that if you have any base to a power divided by that same base to a power, or if you like, a to the n divided by a to the m, you can put those bases together as a single base a, but doing so, you will be subtracting the exponents. That's our quotient rule for exponents. So that's the rule that I want to use with my x's. So I have x, and my top or my numerator right here has a negative 8 as the exponent. So I'm going to take negative 8 minus, and now I take the exponent on the bottom, which is 10. And so I can take those two x's using the quotient rule and put them together as a single x. I'm going to apply the same quotient rule to y, because notice I have y, both the numerator and the denominator. So I'll apply the quotient rule, and I'll take the exponent on top, which is negative 2, and then I'll subtract from it the exponent in the denominator, which is negative 7. And remember, all of this is all going to be raised to the negative 3, but we'll worry about that part after. Okay, so what does that simplify down to? What does that give me? Well, that gives me 1/3 x raised to the negative 18 power, y raised to the, okay, do a little bit of math here with our positives and negatives. Remember, negative back to back actually means positive. So what we have is negative 2 plus 7, right? I have y to the negative 2 plus 7, and negative 2 plus 7 is just 5, and so that's going to give me y to the 5, all raised to the negative 3. All right, so far all I've done is simplified. I've reduced a fraction, and then I've applied the quotient rule to both the x variable and the y variable. But now I have a much simpler expression to work with. I want to continue simplifying this because I need to write my answer with positive exponents only, okay? Okay, so now I have to deal with that negative 3 on the outside. And we have a rule that tells us when we have factors, meaning things multiplied together inside a quantity, raised to a single power, we can distribute that power to each of the factors inside. In fact, that's a power rule for products, right? It's a special power rule that we apply to products. So we have a power rule for products. And what does it state? It says the following. It says that we have a factor a times b raised to the n That's equivalent to taking a to the n times b to the n. So if we have multiple things multiplied together raised to a single power, we apply the power to each factor inside. That's what I'm going to do to this expression. I'll do it right here and then we'll switch to a new slide, but I'm going to take that first factor, 1/3, and I'm going to raise it to the -3. Then I'm going to apply that power rule and take x to the -18 and raise it to the -3. And then I'm going to take y to the 5th and raise it to the -3 power. Now, some people skip doing this extra step and they jump right to the next step, and that's okay. But this is what I have written out. So let's go ahead and make some more space to do this. And let's write our problem out again. Our problem was that we have 1/3 to the -3 power, x to the -18 to the -3 power, and y to the 5th to the -3 power. And we're almost done, but we need to get rid of all the negative exponents and we need to do a couple more simplification steps. All right, looking at this, the first place that I want to start is I want to help get rid of these variables here. I mean, not get rid of them, but let's simplify the exponent on those variables. Why? Because I know there's a rule and a property that allows us to do it very quickly, and that's the power to a power rule, right? Power to a power rule. Meaning, if I have a single base, oh, I'm spelling it all wrong here. All right, so if I have a single base, a, and I have it raised to a power, but then all of that is raised to another power, the power to the power, I can simplify this by doing what? I take the base and I multiply my exponents. So that's what I want to apply to the x and the y variables. I have x to the -18 to the -3. I'm going to multiply my exponents, and that's going to give me 54 as the exponent on x. And I have y to the 5 to the -3. Multiplying 5 times -3 gives me -15. And so I have y to the -15th power. And then, of course, I have this front that I didn't deal with yet, which is -1/3 to the -3 power. One more step. We're almost in the clear. I know this is a really long problem, and it's really cool because it uses all kinds of powers, but here we go. So our last step now is we don't want to leave our expression with any negative exponents. Notice I have x to a power, y to a power, and my coefficient to a power. But let's take care and get rid of the negative exponents. So now what we're going to do is apply our definition for negative exponents. So the definition of negative exponents, it actually comes in two forms, okay? One is when you have a fraction. So like our first guy, 1/3 is a fraction. So if you have a fraction raised to a negative exponent, the way to convert it to a positive exponent is you invert the fraction, right, and make your exponent positive. So if you have a over b to the -n, you invert the inside and make it a positive n. So I'm going to do that and use that part of the negative exponent definition to my 1/3 to the -3. I'm going to go ahead and take, instead of writing 1 over 3, I'm going to write 3 over 1 raised to the +3 power. X is raised to the 54, and that's a positive exponent, so I don't need to do anything with that. But my y is raised to the -15, and I also need that definition of negative exponents to deal with that. And what is that definition of negative exponents if I have a single base and not a fraction base? So if I have a to a -n power, what do I do to get rid of that negative exponent? Well, I simply invert that base a, right, and make my exponent positive. So a to the -n is equal to 1 over a to the n. That means y to the -15 is equal to 1 over y to the 15th power. All right, we are just close, almost done here. So let's put this all together. I have 3 raised to the 3rd. That means 3 times 3 times 3, which is 27. So I have 27 over 1, or if I like 27 x to the 54th, and y to the 15th is in the denominator, so all of that is going to be over y to the 15th. So if I want to clean up my answer and make it especially nice, I'm going to have 27 x to the 54 over y to the 15. I have simplified my original expression and left only positives exponents in my answer. Whew, that was a long one.